In this video, we study infinite sequences and the limits of infinite sequences. What is an infinite sequence? Well, infinite sequence is a sequence of infinite many numbers, like A1, A2, A3, each representing some number, some value. So this list of infinite numbers is what we call an infinite sequence, denoted as A sub n. Well, A sub n represents in general the general term in the sequence. For example, 1, 1/2, 1/3, 1/4. Generally, we expect 1 over n and more. So this sequence is denoted as 1 over n. Now, let's talk about why we study infinite sequences. Well, we really want to study the sum of all those numbers. So, sum of infinite numbers is called an infinite series, denoted as sigma n from 1 to infinity. This is actually what we want to do in the following sections. A sum of infinite many numbers. Because of the involvement of these infinite guys, we want to see actually in this section the limit. We'll explain why. About the infinite series, we care about this value. When infinite many numbers added up, it's very hard to see what the outcome is going to be. Well, basically we say this: if the sum is a finite number, we said the series converges. If the sum is infinity, very easily you add infinite many numbers up, the answer is infinity. Or if it's impossible to determine this value of the sum, we say diverges. The series diverges. So our goal really is to try to determine whether an infinite series, sum of infinite numbers, converges or diverges. Now, how is this related to limit of a sequence? Well, let's see two examples. Say you have, or maybe three. Say you have 1 plus 2 plus 3 plus 4. You can denote using summation notation as sigma n from 1 to infinity. Clearly, the value of this infinite series is infinity, because you keep adding numbers up. The answer is infinity. So it diverges. Now let's see another one. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Well, we can also using summation notation to denote this sum. Can be shown fairly easily. The sum of those numbers added up, the value of these numbers added up, is also infinity. So this series diverges, this series diverges. Notice in this series, the numbers involved are becoming smaller and smaller. As a matter of fact, you can see 1/3, 1/2, 1/3, 1/4, 1/5 approaching 0. So these numbers are getting smaller and smaller, approaching 0. Yeah, some of those guys add up. Some of this guy is infinity. Value of this sum is infinity. Let's say another one. 1 plus 1/4 plus 1 plus 1/2, 1/4, 1/8, 1/16. Well, what we see here, basically the bottom is a power of 2. So it's 1/2 to the nth power. And from, say, 0 to infinity, we take the first term as a equal to 0, n equal to 0, n equal to 1, n equal to 2, and so on. Well, this time, these numbers added up equal to 2, which we can show later on. So, first of all, we say this series converges. Now, here's the question. When we compare those two series, the guys involved all approach 0. 1/n approaches 0. 1/2 to the nth power approaches 0. Yeah, this one diverges. This one converges. What we can see is, one thing we can see is those numbers approaching 0 faster than those numbers. You can see just by comparison. Those guys becoming smaller and smaller faster than those guys in this series. So we suspect converges, diverges of an infinite series. It's probably related to the limit, specifically from what we can tell now, how fast this thing becoming 0. At any rate, we need to check out the limit. As a matter of fact, later on there will be test actually says limit as n goes infinity of a sub n equal to 0 is a necessary condition. So it's not just, it pushes 0 or not. It's necessary plus maybe how fast the sequence approaches 0. So this is one reason we want to examine limit of sequence. Also later on, when we introduce different tests that we use to check convergence divergence, we'll do limit. This is why in this section we want to talk about infinite sequence, particular limit of infinite sequences. Well, infinite sequence usually is some expression involving n, like the one sequence we have, a sub n equal to 1/n, or a sub n equal to 1/2 to the n, or other case, say a sub n equal to 2n plus 1/5n squared plus 2. It's basically some expression involving n, like what we say here. How do we check the limit of sequence? Well, let's recall how we do limit. We learned to do limit of a function x approaches whatever, or in this case let's just say x approaches infinity. For example, we can do table method. We set up table. As a matter of fact, we learned Lorbita's rule. There's a fraction, or sometimes we estimate. There are a number of ways available for evaluating limit of a function like f of x. Actually, a sub n in general, like you can see, is some expression of n. It's a function. The difference between this kind of function and the traditional function is traditional function contains a continuous variable x. X takes all values. Well, this is a new type of function. It's still a function because given n, we can calculate and come up with output. So different n, different output, different n, different output. So this is mathematically is definitely a function. It's just the function contains a discrete variable, meaning n takes those values only 1, 2, 3, 4, 5. Unlike x takes all values on number 9 in the domain. Well, what's the difference between limit of sequence and the limit of function? Let's see. Take this as an example. Say we have a sub n 1 over n. Let's see a function, a related function, 1 over x. Well, n is a discrete variable, x is a continuous variable. What's the difference between the limit? N goes to infinity, x goes to infinity. Well, you'll see there's not much difference in terms of limit. Number 9. Let's graph 1 over x. Let's graph 1 over n. Well, x takes all the values. In 1 over n, n takes only 1, 2, 3, say 4. So the graph of 1 over n as a function would consist of those dots. Graph of this function, obviously the whole entire connected red graph. So let's check out the limit. Along the graph, as x approaches infinity, the function value along the curve approaches 0. So we get limit of function. Now let's check the limit of sequence. This time we're going to go along those dots, like jumping from this point to this point to this point to this point. Well, in the end, the limit is 0, 2. As a matter of fact, we can show in general limit of a sequence consider as some expression of n. It be same as limit of a similar function. Well, the variable n is regarded as a continuous variable x. That's what we see here. So this means In order to check the limit of a sequence, we could pretend the n to be a continuous variable, assuming such function exists. Well, if we do this, all the ways we learn to evaluate the limit can be applied. For example, if we have a sequence that's a fraction, and we check, this will approach infinity, this will approach infinity, we can apply L'Hopital's rule. In determinate form, we can apply L'Hopital's rule. Now, in order to apply L'Hopital's rule, of course, for example, let's just be specific. Say this 2n plus 1 is a 5n squared plus 2 we had. Or you can check n goes to infinity, this will approach infinity, this will approach infinity. Now, if n is considered as a continuous variable, we can differentiate. Otherwise, we cannot differentiate. Discrete function is not differentiable. Discrete function, not even continuous, connected. So, any x of n, suppose we can think of it as a function of n or simply function of x. We can do limit the way we learned before. We can evaluate the limit like before. With one condition, it would have to be actually a function. Sometimes, for example, you have a sequence negative 1 to the n to the power 1 over n. Well, this time you cannot treat n as a continuous variable because there's no such function. This part doesn't make sense, but most of the time we can do it. So we'll just learn, how to evaluate limit of different sequences. Sometimes sequences can be treated as just a regular function. If not, then we'll see what to do. Now, before we see examples, we need to know some results. Here's one theory, which is based on the sandwich theory or squeezing theory. This says if somehow we find limit of sequence 0 and a sequence that's bounded, in other words, absolute value of these numbers is never more than some fixed number, we call it bounded, then limit of this product is 0. We're not going to see the proof. This result is based on the squeezing theory or sandwich theory. And we'll actually use this result to deal with this kind of factor. Because you can see negative 1 to the n to the power, if you take an absolute value, it's never more than 1. So we have this kind of estimate. That's treated like a Bn. We see this kind of stuff. Sometimes bounded power approaching 0. The product will approach 0. That's basically what this theory says. It's based on squeezing theory or sandwich theory. Now, there are some results we want to talk about. They are simple, limited results. We can prove very easily. These are very common, so we're going to just take them as known result. Okay, here, end power, basically, end power of a number. Well, we're mostly interested in the case when the absolute value of it is less than 1. Absolute value at the base, b. If the absolute value of the base is less than 1, b can be positive, b can be negative, like a negative 1/2, positive 1/4. The limit is 0. Another interesting result or useful result is when r is more than 1. B, when the b is more than 1, the limit is infinity. The other cases too, as you can see, for example, b equal to -1, b equal to +1, we don't usually run into these cases, so we don't need to worry about them. Just remember two cases. Value. The value is more than 1, the limit is infinity. If the absolute value of the base is less than 1, the limit is 0. So we'll use this result sometimes to quickly come up with our answer. And this result can be easily proven, so we're not going to get into that. Alright, now let's see some example. Okay, limit of sequence. Here our sequence is n squared minus n plus 7 over 2n to the third power plus n squared. That's a sub n. So what's the limit? Well, look at the sequence a sub n. If n was replaced by x, continuous variable, this would be a rational function, well defined. So we can treat this as like a standard function involving continuous variables like n for the purpose of finding limit. Well, if n is continuous variable, this is what we consider as an indeterminate form, because n goes to infinity, this will approach infinity, this will approach infinity. It's infinity over infinity, L'Hopital. We can apply L'Hopital twice and get the answer, or we can actually, better yet, drop lower order. This is a shortcut we learned in dealing with the terms approaching infinity. We can compare order. 7 is lower order compared to n squared. N is lower order compared to n squared. So we drop actually both of them. Similar at the bottom, we can drop n squared. N squared is lower order compared to n to the third power. We can do this, and then cross out n squared. When it goes to infinity, this goes to 0, so get the limit right away. Or we can actually start from the beginning, just say the top goes to infinity as a square, bottom goes to infinity as a third power, bottom is a higher order, top is a lower order, so the ratio will approach 0. We get the answer that way too. When it's considered as a continuous variable, there are a lot of things we can do. There's a lot of things we learned to do before. So limit of this sequence is 0. Let's see next example. N goes to infinity. Well, n goes to infinity. What about this guy? Well, log n goes to infinity too. Recall the graph of log. As n goes to infinity, the graph goes up, keeps going up, approaching infinity. So it's infinity over infinity. We can apply L'Hopital rule. Better, we'll just compare order. Basically, the top goes to infinity as a log, which is a lower order compared to power of n. This is the first power. So we can draw the conclusion right away. The limit is 0 because the bottom becomes larger, faster than the top. You may be wondering, yeah, log n is lower order compared to n. How about the square? Well, that's easy. We can always just say split the top as log n times log n, and bottom split as half power. This way we can compare like that. So to still, log n is lower order compared to power, positive power, any positive power. Log n, so it's 0 times 0. That's 0. So this says it doesn't even matter what kind of power you have for log. When it's compared to power of n, it's still lower order, because we can, as you can see, just split accordingly. If you apply L'Hopital's rule, you can get the same answer too. So compare order is probably the easiest way to get the answer. Now let's see this limit. Our sequence is sort of exponential. Think of n as a continuous variable. So this is like one of those indeterminate form. Indeterminate form in exponential form is done by converting to a new exponential to base e. Now we just focused on the exponent where n changes, the base is not changing anymore. Before, in this type of indeterminate form, both the exponent and the base change. Right? We cannot deal with this kind of exponential directly. So by changing the base, we focus on the exponent. Exponent now basically is a fraction. You can do the algebra, or you can just flip 1 over n. If you flip 1 over n, put the bottom, it will be like n on the bottom, so it's the same thing. Or you should do simple, put it in the denominator. Now check, n goes to infinity, log will approach infinity, n will approach infinity, so it's infinity over infinity. We can of course apply L'Hopital's rule. We can also compare order, lower order versus higher order. Power is higher order than log, so we say the limit is 0. Compare order, or let's apply L'Hopital's rule for a change. The previous examples, I pretty much always compare order, get the answer. And this time, let's actually apply L'Hopital's rule. So we differentiate the top, 1 over 2n plus 5 times 2, that's logarithmic rule. Bottom, derivative of n is 1. This is applying L'Hopital's rule. Now when it goes to infinity, this will approach 0. 0 times 2 is 0. 0 divided by 1 is 0, so it's e to 0. Like I said, we could have get the result right away just by comparing order, log being lower order compared to n. The limit will be 0. So overall the limit is 1. Let's see another limit. The sequence is a fraction, 2 to the n plus 1 over e to the n. Apparently, we just estimate the bottom approaches infinity, top approaches infinity. So we have actually an indeterminate form. Now I don't want to apply L'Hopital's rule because the derivative of 2 to the n is a little bit more complicated. Plus, the idea is, if you differentiate the exponential, you pretty much always get the exponential itself. So it's we still have to deal with exponential on the top, exponential on the bottom. So we're not going to apply L'Hopital. So instead, we try to make use of this result. Not directly. If we do it directly, we're not getting anything new, because this would say, oh yeah, this is going to approach infinity. Base is more than 1. This will approach infinity, infinity over infinity. Instead, we'll do some algebra first. We'll do termwise division. So it's 2 to the n, e to the n, 1 over e to the n. This is dividing 2 to the n by the denominator, 1 divided by the denominator. Now, the first term can be rewritten as 2 over e to the nth power, and this as 1 over e to the nth power. So for each, I can tell the base is less than 1, 2 over e is less than 1. So this could approach 0, and 1 over e is less than 1, it's approach 0. This is because of the result we had. When the absolute value of the base is less than 1, nth power will approach 0. This is the reason I'm showing you this example. I want to make use of the known result, and we see this a lot. Alright, finally, let's see a limit. Well, we'll use the sandwich theory. If you just estimate, it's not clear how to find the limit. N goes to infinity, this will approach infinity, or this will we're not approaching anything, because the sine graph goes up and down. If you square it, you pretty much get that everything will become positive. You'll get this kind of thing. So up and down, it's impossible to determine the limit. So how we do this one is to actually split as one factor, the square of sine as another factor. Now this is what we consider as the a sub n, this is what we consider the b sub n. Clearly we can see a sub n approaches 0 when n approaches infinity. Well, the b sub n, it's absolute value of sine, that's always less than or equal to 1. So we got the perfect combination like this. I have a factor approaching 0, other factor always bounded according to the theory, which is result of sandwich theory. The limit of the product is 0. So we just draw the conclusion. So roughly speaking, we're saying this guy gets a smaller approaching 0, where this guy is always kind of finite number, more or less, like a 1. At the largest, at the smallest is 0. So it's a finite number. 0 times the finite number is 0. That's really what this theory says. But then we have to verify, but to actually be sure this part will approach 0 and the other part will be bounded. When can we apply actually this theory? Not often. The thing is, we don't know how to estimate a lot of expressions. Commonly, if we see sine, cosine, or negative 1 to the nth power, we most likely will probably do it this way, because those are the only bounded guys we can easily show. There are many other bounded expressions, just not very obvious how to prove it. The sequence is, we do, if we have to use the sandwich theory, it must be sine involved, maybe cosine involved, maybe power of negative 1 involved. So that's kind of clear. Otherwise, we just treat it as an expression containing continuous variable. Apply L'Hopital's rule. We compare order terms, drop low order term, or if it's in exponential form, change base, this kind of thing. Alright, this is infinite sequence and the limit of infinite series.